Hi, and welcome to Allen High School's discussion of acids and bases at the pre-AP chemistry level. Now, we've just begun our discussion, and let's introduce the key players in this game. Now, one is called a proton. It's hydrogen without an electron, and it is symbolically equivalent to H3O+. This is just water plus the proton, right? If I took H2O and added an H+, I'd get H3O+, and those are considered equivalent. And the other player is the hydroxide ion. Now, both of those are present to some extent in solutions. So what we're looking at here is a balance between the two. So if we have a pH below 7, and you should be familiar with the pH scale, so I'm going to treat it as if it's not something totally new to you. If we are less than 7, at that point H plus is greater than, it's winning kind of this balance between the two, greater than the OH minus. So you can really think of these as a balance, sort of like a teeter-totter effect with these. And when it's acidic, there's more H plus than there is OH minus. Okay. Now, when it's basic, when I go above 7, when it's greater than 7, at that point, my hydroxide is heavier or winning the teeter-totter kind of balance over the H plus. Both are present always to some extent. It's their relative amounts. Now, in a neutral solution, H plus is equal to the OH minus. So let's take a quick look at definitions. If we're talking about an acid, again, this is just saying the same thing in words. It was written in the notes that an acid has H plus. I really don't like the way that is phrased. I really like an aqueous solution is one in which the H plus is greater than the OH minus because something like HCl has been added. Now HCl can donate H plus to the solution, and we'll see that in just a moment. A base, so if we have a basic solution or a base, it's a solution in which the hydroxide is greater than the H plus. Okay, that goes in that tiny little blank. I know it's not much, but the key is the hydroxide there, and it's also called alkaline, kind of like alkaline batteries. Now the alkaline metals, group 1 metals, are called the alkaline metals because they form bases in water. The group 2 metals are called the alkaline earth because they also form bases in water. All right, we have 3 theories that we're going to be talking about, and this is the most narrow. So they're kind of a set. So we'd have Arrhenius is the most narrow, and then Bronsted-Lowry, which is where we're going to focus most of our time, is Bronsted-Lowry, and then Lewis is the most broad. Now, in this case, an acid is something that ionizes to form hydronium in water. Hydronium is H3O+, and remember, it's symbolically equivalent to H+. This is reality. This is shorthand. Okay, that's basically what it is, effectively. I shouldn't use that word basically when we're talking about bases. Effectively what it is. Now, a base is a substance that forms hydroxide ion in water, dissociates to form hydroxide ion. Now, unfortunately, Arrhenius doesn't account for most of our weak bases that are centered on nitrogen. And so that's why we move into the Bronsted-Lowry definition. In the Bronsted-Lowry definition, an acid is a substance that donates, it's a subtle nuance but important nuance, donates a proton. Okay, so this is the acid, it's donating a proton to the water. This is called its conjugate base. What's left after the acid does its donating is called the conjugate base. Now, a base is a substance that in turn accepts a proton. Doesn't just ionize to form OH minuses, it accepts a proton. Okay? Now, up in this case, actually hopefully you see, do you notice that H2O accepted that proton? So water was the base here, and H3O would have been its conjugate acid, H3O plus. What's remaining after bases do what bases do best is called its conjugate or paired acid. Now in this case, the water is donating to the ammonia. So do you notice that the ammonia gained in going from here to here, the ammonia gained both an H and a plus charge. So the ammonia is the base. The ammonium is called its conjugate acid. So ammonia is the base. It formed NH4 plus, which is its conjugate acid. Water acted as an acid in this case, giving up an H and a plus. So this is its conjugate base. So this lost an H and a plus, and this gained an H and a plus. Okay, so start getting us into some of that terminology. And we use a double arrow here because it's weak. Single arrows go 100%. Double arrow is, we're going to see as an equilibrium, and it goes less than 100% to product. Lewis theory, you only have to know at the definition, so you just have to memorize it so you realize that we have different ways of describing processes. In this case, an acid is an acceptor. Remember in Lewis, the acid is the donor. In Bronsted-Lowry, so in Bronsted-Lowry, the acid is the donor and the base is the acceptor. And we're dealing with electron pairs. In Lewis, it is the acid that is the acceptor. Oh, Dina, I messed that up. Bronsted-Lowry. Sorry. Get this straight. I'm going back and forth and messing up. H plus. Bronsted-Lowry's dealing with donating and accepting an H plus. Lewis, the acid's the acceptor. The base is the donor. Do you see how that's opposite? And it's Lewis that loves electrons. And so this time we're talking about electron pairs. So I wanted you to see that comparison. Sorry about that mess up. Bronsted-Lowry, acid donor, base acceptor, focusing on H+. Lewis, acid acceptor, base donor, focusing on electron pairs. So in this case, ammonia has that extra electron pair. It can donate to the boron to make that bond. So boron's the Lewis acid, and ammonia is the Lewis base.